All right, Ryan.
Okay.
Easy. Just make sure you do it.
Perfect. Yeah, we're good to go.
All right, welcome. Can everybody hear me online? Shannon, can you hear me okay?
I can hear you perfectly.
Okay, awesome. Thank you, Shannon. Thank you, Andrew, for the introduction. I appreciate it. My name is Ryan McCoy. I'm with NTS Innovations, and tonight we're going to talk about what NTS is working on, graphene energy harvesting. Go ahead and go to the next slide, Andrew. NTS is a nanotechnology company. We focus on bringing science and partnering with universities and basically taking stuff that's being worked on in the laboratory into the marketplace. Our motto is tiny scale, massive impact. Tiny scale because of the nanotechnology, and massive impact because of the applications that we're going to be bringing this technology to. A lot of implications for a lot of industry. So I want to talk a little bit about our leadership. Andrew, you can go to the next slide. We have two of the three of our leadership team is from Central Illinois, like myself. Don Meyer, our founder, is a serial entrepreneur. He's always seems like he's thinking 4 or 5 years into the future, which is why he founded a nanotechnology company. He's an inventor, innovator, a lot of active brands that are sold nationally, and he's a contract manufacturing expert. We've also got Tom Bazell. He's our COO. He comes to us after a long, successful career at Caterpillar. So he brings a lot of knowledge about scale and enterprise to NTS. And then Preston Carter, he's the odd man out. He's based in Austin, Texas. He's our CTO. A lot of experience managing deep technology projects at places like NASA, Lawrence Livermore Laboratories, and DARPA. So we're very lucky to have him. Go ahead to the next slide, Andrew. What I'm going to talk about tonight would not be possible without a great partnership with the University of Arkansas. So I mentioned NTS. Our premise is we partner with universities to commercialize products. And we've licensed a technology that was developed at the University of Arkansas, and we're collaborating with them to get to a commercialized product. So graphene energy harvesting, what is it? Let's first talk about energy harvesting. So if you think about a calculator, for example, that's got a solar cell, that's probably the earliest example of energy harvesting. I've also got some in my watch here as I move my.
Pause for a second.
Yeah, go ahead.
It looks like I have to reshare. Sorry about that.
No problem.
I'm gonna have to reshare the slides. Okay, I think that works right now. So very quickly, Sean, just want to go through again.
Yeah, I can go through again. So NTS, science-to-commercialization company. We work on bringing stuff that's in the laboratory to the marketplace. We've got awesome leadership team, Central Illinois based, 2 out of the 3. And we are partnering with the University of Arkansas to bring graphene energy harvesting to market. So it's a super exciting technology. If you go ahead and advance to the next slide there, Andrew. So energy harvesting, I think I was talking about my watch, right? So in my watch, I've got a technology that as I'm moving my arms, recharges the battery. That's another form of energy harvesting. So there's existing examples out there where you're taking environmental inputs and converting that to electricity. But graphene energy harvesting is unique in that it isn't tied to one specific input. And we'll get into that a little bit more. And the way we're accomplishing that is by sort of combining 3 different disciplines: nanotechnology, material science, and semiconductor manufacturing to bring energy harvesting to the chip level. So let's talk about the nanotechnology aspect. Nanotechnology is sort of manipulating things on the scale of atoms. Does anybody want to take a guess at how many atoms they think are in a droplet of water? It's a big number. I'll let you in on that. Yeah, so that is a 5 with 21 zeros. If you go to this website, thoughtcode.com, they will tell you exactly how they calculated that number. I'm not sure if that's scientific fact necessarily, but the point is atoms are tiny. They're very, very small. And when we talk about nanotechnology, that's the level that we're operating at. Next, we'll talk about material science. So graphene is one of the world's first two-dimensional materials. So if you look at the thickness of graphene, a single layer of graphene is only 1 atom thick. So we just talked about how small an atom was. It's kind of mind-boggling to think that something can exist at that level of thinness. But it's also got some really unique characteristics. It's got a tensile strength that's much stronger than steel. It's one of the world's best conductors of electricity and heat, and it's also flexible. So if Andrew hits the next button, we're going to see an animation here of what graphene would look like at the nanoscale. And so
Anywhere?
I think you just advance, Andrew, and it should, well, maybe not. Go ahead and go back. If this was playing, what you would see is that the rippling of the graphene would sort of look like waves in an ocean. So it would constantly be moving up and down. Those atoms are sort of getting bombarded by lots of things at nanoscale. So temperature changes, vibration, RF energy, radiation, all those things are acting on the atoms and causing them to move up and down. And so if we suspend graphene where there's nothing touching it on the bottom and nothing on the top, you get that wave-like motion at graphene. And that's the phenomenon that we're taking advantage of to create a nanoscale energy generation system. You're probably thinking, well, how in the world do you build something that's that small? And the answer is with semiconductor technology. So 50, 60 years ago, it wouldn't be possible to build something like this. But because of the way that semiconductor manufacturing has advanced, you can go to the next slide, Andrew. We can now build things that are this small. If you look at Apple's chip that they put in the latest iPhone, there's over 1 billion transistors on that chip. So they're able to create very, very tiny features using semiconductor technology, and that's the same technology that we're using to build graphene energy harvesting. So a little bit deeper about how the mechanics actually work. So let's compare it to something like wind power. So we're all familiar with wind power. There's some similarities and some differences. So in wind power, you've got the wind that's acting on the blades of the windmill. That's connected to a generator, and then the generator spins, creates electricity, and that's sent to the grid. It's a really similar flow of events with GEH. So instead of wind, we've got nanoscale noise, all those things that are acting on the atoms of the graphene membrane. The graphene membrane takes the place of the blades of the windmill. And then that's connected to a graphene energy harvesting circuit, very, very tiny circuits that then get arrayed in a small area and work together to charge a capacitor or a battery or device. The differences between GEH and wind power are, of course, that we can do all this in a very, very small area. So there's energy density advantages, and we can put GEH in places that we can't put other forms of energy harvesting. The other thing is with wind power, you need wind to be blowing. And with graphene energy harvesting, there's always things that are interacting with the membrane to cause it to move. So our vision is bringing all of this to the device level, to where we're actually generating electricity on a device. So we're aiming for a first generation chip that's about the size of a dime and can be plug and play on printed circuit boards, which is the basis for all electronics. Works in all environments, clean, efficient, reliable, because there's always energy harvesting taking place, and it's very scalable because we're using semiconductor manufacturing to produce at scale. So this event tonight is about IoT devices. We feel like this technology is eventually going to make its way into a lot of things, but it's hard to find a better use case than IoT devices or wireless sensors. And there's a couple reasons for that. Number one, there's a very well documented pain point for IoT devices. A lot of device manufacturers trying to figure out ways to reduce battery life, reduce battery usage and increase battery life. Because there's a lot of innovation happening in this space, the time to market with IoT devices is relatively short when you compare it to something like medical devices or cars or computers. And then there's just lots of them. coming online, lots of IoT devices. And so it presents a good opportunity, a good starting point for NTS to implement GEH into these types of devices. So we're going to show a video now. I hope it works. This is one of my very favorite use cases on battery life and why you might want to have a self-powered type of device as opposed to one that's powered by battery. So it's not working. No worries. I can walk you through what's going on here. And if you want, we can probably send you out the slides after the deal here. But in this clip, they're going to show the Burj Khalifa in Dubai, tallest building in the world. At the very top of that building, there is a lightning system that detects thunderstorms and kind of warns people that there's an approaching lightning storm. Well, the sensor in that lightning system cannot be connected to the grid. It's got to be independent, and so it's powered by a battery. So periodically, the technicians have to climb up the spire at the very top of the world's tallest building just to change the battery. And it's a pretty tall tower. I think it's 80 feet that you have to climb up that spire just to get to the point where you can replace the battery in that sensor. So that's kind of an extreme case, but it highlights the value of having self-powered sensors. If you go to the next slide, we can talk about a couple more. Think about smart buildings. If you had, let's say, a radiant heating system that was buried in concrete and you wanted to monitor the performance of that radiant heating system with sensors, you wouldn't want something that's battery powered, obviously, because once you put it in concrete, it's embedded. Same thing with ductwork that's behind walls. If you wanted to measure airflow through ducts and things of that nature, self-powered IoT has a great use case for that. Think about agriculture or maybe a factory type scenario where you have hundreds of sensors that are spread out over a wide area. The labor involved with changing out the batteries in that type of environment is very cumbersome and expensive. And then consumer devices as well. We've got an advisor who has a vacation home in a state that's a couple states away, right? So he's not always there. He told us the other day that he got a notification on his phone that the door sensor on the front door was out of battery. So he wasn't going to be back at the location for a couple months. And so he had to make a choice. Do I wait a couple months with a security sensor that's not operational? Or do I make an emergency trip to a couple states over to change the battery? So just a couple of use cases where self-powered IoT is very useful. So how close are we to bringing this to market? Well, NTS is deep into an iterative R&D process at the moment. So it kind of looks like this. We come up with a chip and circuit design. We ship that off to a foundry. They're going to take a piece of silicon oxide like this and manufacture the design on the silicon oxide. And then they send the chips back to us. Sometimes they're packaged. Sometimes we package them at a third party. And they come back to us looking like this. We're currently doing this type of packaging. I'll pass these around so you guys can see them, but the active ingredient is the little piece of silicon there. The package that's surrounding it is so we can plug it into a breadboard and run testing on it. But you'll see as I pass this around kind of the scale, how small it is that we're working. So we test the chips. They return us some results. Usually there's some things that we do right with the design and some things that need to be improved. And so we restart the design process. And that's something that we just submitted our latest design to the foundry about a month ago. And so we're waiting for our next batch of chips to come back. So some things that have happened in 2021 that we're pretty proud of, some milestones. Go ahead and flip there, Andrew. In February, we participated in a DoD Energy Challenge. So we submitted alongside lots of other companies, and we were in the top 18% of companies that got selected for this challenge. We're able to showcase this concept to the DoD, and that event is still yielding some fruit today. We are to the point now, if you rewind about a year ago, let me start there. Rewind about a year ago, what we could do in the lab is we could take a chip, and we could hook it up to a laboratory amplifier to kind of simulate how that chip would behave if there was lots more energy harvesting circuits on the chip. Well, this year we're to the point where you see the chip in the picture there. That's not a dip package. That's a commercial package surface mount on a PCB that's a little closer to what our customers would be looking at. And we're able to measure very, very small levels of voltage and current without the laboratory amplifier. So that was a big milestone that we achieved this year. We demonstrated this at a startup showcase at the University of Arkansas. That's a picture of the demonstration that we did there. Another goal we had this year was to bring manufacturing to the US. A lot of semiconductor manufacturing is happening overseas. This year we were able to establish a relationship with the US-based foundry, which has its advantages. And then we also have continued to engage with customers and influencers and partners, and that list has just exceeded 100 parties that are interested in working on this with us. So a lot has happened in 2021. What's next for NTS? We've got, you can click to the next slide there, Andrew. We're expanding into a new space at the University of Arkansas. So we had a small laboratory space there. In previous years, we've expanded to a second building there, which is going to help with testing and collaboration with the university research staff. We are hiring as well. So we've got 2 open positions in the semiconductor engineering space. ntsinnovations.com/careers if you want to check those out. And as I mentioned, our latest prototype is underway. That design has been submitted to the foundry. And the goal of all of this is we're looking to get to a point where we can pass our chips on to customers and they can begin playing with them in applications. We've mentioned that list of 100. We've got about 5 so far that we feel like are really well positioned for beta testing and have committed to when we get to a point where we're harvesting enough energy for them that they're going to do beta testing for us. And that, so that's right around the corner for us as well. So a lot of exciting stuff. I went through that very fast. So we're to the point now where we can open it up for questions. But yeah, thank you for listening, and happy to answer any questions about graphene interconnectors.
So you say it's R&D, and I get that.
Yeah.
What are the design goals that you meet in your success? So has it got to be producing enough energy to charge an iPhone in a day, or?
No. So what our original design goal for the GEH Generation 1 chip was 10 milliwatts. And we're still aiming for that. We think we can get there. But what we're finding in talking to a lot of customers is that 10 milliwatts is more than enough energy to do what they need to do with wireless sensors. So what we're finding is if we can get 1 microwatt of power, then our customers can do beta testing with that. So 1 microwatt is basically 1,000 times less than 1 milliwatt, right? So there are a lot of applications out there where you don't need a lot of power to do proof of concept work.
So assuming 1 microwatt or thereabouts is where it hits commercial. Oh, sorry.
So we're very close. We had the latest chip that we got back in August, right? The one that we showed at the University of Arkansas. We had anticipated that there was a chance we would get there to the microwatt level. We did not. But this latest one that's in the foundry right now, we feel pretty good that has a chance to get there. But long story short, we're learning something every time we do a development cycle and development iteration. So, very likely that it could be as soon as a few months. Also possible that, if those designs don't work as well, that it would be longer than that, but it's very close.
So we have some questions online.
Yeah.
If you wouldn't mind repeating the question because the microphone's by you. The first question is, Zach is wondering about thermal insulation and whether the heat from the interaction between the atoms and graphene affects the efficiency of harvesting electricity.
So one thing I will say that we do have to deal with is parasitic capacitance. So when we're putting circuits very, very close to each other, that's one thing that we have to design for. Heat isn't as much of a, thermal isn't as much of an issue. It's more related to how close we're putting circuits to each other, and we've got to deal with the impedance and parasitic capacitance.
I have a couple questions.
Yep.
What is that turnaround time in your iterative?
Yeah.
Repeat the question.
So yeah, so Phil asked, what is the timeline from the time that we submit a design to the factory, essentially, to the time that it comes back to us, we do the testing. So typically a design cycle for us is about four to 5 months. 4 to 5 months. Yep. And that includes the design, that includes the shipping to the foundry, and getting it back and testing and understanding what we received from the foundry. So there are ways to shorten it. Absolutely. Working with multiple places is one way to shorten that.
There are others who are going to market with graphene and energy harvesting. But it's now in apparel and garments. Going to market. So that's practical use that's already in the market. So the question is, you're focusing on this with that, which is pretty well, and go fast.
Yeah, no, absolutely. It's a great point. Phil basically said that he's just reiterating that speed to market is important. And are there ways to speed that up? The answer is yes. That, you know, if we work with multiple foundries, for example, is one way to speed it up.
Some more questions online. Is GEH or graphene energy harvesting in any way related to 0-point energy?
No, it's not. I've seen 0-point energy. I don't know too much about it other than it seems more based in science fiction than science, I guess. So, but no, we wouldn't call graphene energy harvesting 0-point energy.
And
Or
so
anything
for the
close to
benefit
that.
of everybody here who may not know what 0-point energy, maybe you can share a little bit.
Yeah. Honestly, the most I know about 0-point energy is there's a company out there. I can't remember it off the top of my head, but if you Google 0-point energy, you will find a company that's working on something like that. And that's probably a better source of information than me trying to explain what it is. But I will just say that graphene energy harvesting is not 0-point energy.
Perfect. One more question here from Kim. Can you talk a bit about durability? For example, can you hang it on a pet in all possible conditions?
So the question was durability of graphene. Can you count on it to work in lots of different applications? So what I can say to that is graphene is a very durable material. You know, I mentioned the tensile strength in the presentation. It's very strong at nanoscale relative to other materials at that level. The key for graphene is you need to package it correctly. You need to protect it. So if you look at the chips that are going around, you know, these are experimental packages, right? So they're packages that go on the breadboard, but you can see there's covers over the top of it. They're pretty well protected. In that commercial version of the chip that I showed you, that's a surface mount, that is also packaged as well. And there's lots of different levels and robustness that can happen on a commercial level. But the key is that you encapsulate the contents of the chip in protective packaging.
If you were to get 1 microwatt of a dime-sized chip, what percentage of the available energy would you be harvesting?
That's an excellent question. I don't have the answer to that question off the top of my head. So he asked, at 1 microwatt, what percentage of the available ambient energy would you be harvesting? And it's a tricky question because the available ambient energy changes, right? So different temperatures, it's different. There's different electromagnetic radiation floating around in different places. So That calculation, I don't have an answer to on what percentage is available. I will tell you, to kind of get at your question, is how far can this scale up, right? And there's really two ways that it can get more energy dense over time. And that's by putting more energy harvesting circuits in the same amount of area, same footprint. As you go down the scale in semiconductor manufacturing technology, you're able to make smaller and smaller feature sizes. And then the other way that this can be scaled up is that, like batteries, we're designing chips to be able to be put in series to increase voltage and parallel to increase current. So you can put multiple chips together to increase the power level that you're able to produce.
So your iterative engineering is less trying to increase energy density than to scale it up more in engineering.
His question was, in the iterative process, is the goal to increase energy density, or is it to scale up in other ways? I would say each design cycle really has one of two goals, or sometimes both goals, is to either increase the efficiency of the components that we're using in the design, or it's to increase the amount of features that we can put on the specific chip, and that has to do with energy density.
Thank you.
So what are the real world applications at 1 microwatt energy?
So think tiny sensors, right? Things that are measuring temperature, things that are measuring movement. Yeah. Things that measure humidity, those type of things. So they're in an industrial environment. I can give you an industrial example where a machinery might have bearings or something that needs to be monitored, and that machine is giving off a signal of how healthy it is, how healthy those bearings are based on a vibration signal, right? So someone could maybe monitor the health of that machine with a sensor that is looking for a vibration frequency. The important thing there is that you're taking lots and lots of data points. And so as you scale up in energy availability, you'll be able to collect more data points. So I think early on, we're best suited towards applications that don't need to take a reading every microsecond, for example, right? So we'll look at applications that need to collect data points or need to send data points off at a lower frequency, is where we'll start in the IoT arena.
More questions online. Shannon is asking, do you have customers that have pre-ordered? Do you have a pre-order list?
So we have a pretty extensive list of customers that want to beta test. We've, as I mentioned in the presentation, and I'll repeat the question, by the way, I keep forgetting to do that. Shannon asked, is there an extensive list of customers that want to pre-order or have placed pre-orders? And I will say this, we have an extensive list that have requested development kits. So the first thing that's going to sort of be the thing that happens before an order is we're going to make development kits available that can go to engineering teams. So they'll be able to figure out what they can use graphene energy harvesting for. That's sort of the first step before an order. So we do have lots of requests in for development kits. I also mentioned that we narrowed the list down to about 5 companies that we feel are best suited for beta tests. And pre-orders have not been part of that, but we do have agreements that they are willing to beta test orders coming after the successful beta test.
Follow-up question, actually another question from Raj. What is the cost criteria compared to current technology / battery longevity?
Yeah, so that's a good question. So the question was, what is the cost of GEH versus the cost of battery? I will tell you that early on in the life of these chips, we are anticipating that the cost is going to be higher because we'll produce them at lower quantity. But when we get to scale, we're anticipating that that incorporating GEH into a device is going to increase the cost by $20 to $50 per sensor. That's at scale.
Then next question from Zach again. How many layers of graphene roughly will be needed for 1 microwatt?
So the question was, how many layers of graphene will be needed to produce energy at 1 microwatt? The layers of graphene do not necessarily contribute to the power density. So there's a couple things there. Ideally, we want to use monolayer graphene, which is a single layer of graphene. Graphene doesn't always come that way. Sometimes you get multiple layers. The stuff that's been tested in the lab, in some cases has been multi-layer, and that has not contributed to an increase or decrease in performance. But it doesn't work to where you just stack layers of graphene and you get more energy. That's not what happens. It's more related to the number of energy harvesting circuits that you can apply to the chip. So a good way to think about it is more energy harvesting circuits that we can fit into a dime-sized footprint, the better the performance is going to be.
Let's talk about sort of like layman application perspective. Like, what is the impact for the everyday person in, when you're going to be proving this out over time? What is the impact that, everybody living here in Peoria could see?
Yeah. So that's an excellent question. IoT, sometimes it's hard for the general public to understand how IoT is benefiting them, right? The cool thing about IoT is we're collectively gathering information on how we can design better cities, how we can design better buildings, how we can increase the efficiency of the things that we do on a daily basis. So initially, when graphene energy harvesting first comes on the market and is able to make it into devices that become self-powered, it's just going to improve the number or increase the number of sensors that are out there collecting data. That's going to improve the data that collectively everyone is gathering and using to make better decisions. So that's initially how you're going to see it impact the everyday person.
Any last questions?
If the graphene is generating its energy from the atmosphere, activities in the atmosphere, what happens? Go back to using it as an application for monitoring bearings, right? When those bearings go out of ground, it's going to be more energy generation. Is that going to affect the sensors that are always
Yeah.
create spikes?
Yes, absolutely. So the question was, with graphene membranes, and you put a sensor or an energy harvesting chip in a different environment where there's more environmental input, is it going to change the energy output? And the answer is yes, to a degree, right? So you will have that graphene membrane potentially flipping its orientation or more rapidly rippling than it would be in a less noisy environment. And that would contribute to an increase in energy production. Yeah.
So does that threaten the survivability of it? Does it lessen the life?
No, because of the way that that we're setting parameters for how far the graphene can move, there's going to be boundaries that it can move under, and so the amount that it's moving or the frequency at which it's moving isn't going to increase the life of the system.
I have a follow-up question.
Yes.
So, this graphene is vibrating or like a wave in the nano scale. Will it break over time, or will the circuit in the device sensor fail first?
Right. So Andrew's question was, as graphene is moving, does that decrease its life? Is it like a friction type part where you would expect the longer that it's in operation, the more likely it is to break? What I will say about that is if I were to take a piece of graphene and pull it apart with the tweezers, I could rip it, right? But the way that it's going to be implemented in the chip is it's going to be secured in a way that it can move from environmental inputs, but because it's encapsulated or protected into a chip, it's not going to have that same force of somebody pulling it apart with tweezers. And so the expectation would be that that graphene component, even though it's moving very frequently, that it would last as long as the other electrical components in the system.
Thank you. Any last questions? Oh,
Always last. So with the increased vibrations, right?
Yep.
Let me get this question back. I like that back. What is the fail? What are the projected failure rates? Like, the more vibration you're expecting, that somewhere along the way you threaten the security of your stabilizers or whatever you're using to hold your graphene. So again, if you go back to the bearings, I've dealt with bearings a few times. And once that vibration gets to the point where it's breaking the stuff that the bearing is controlling, does that weaken the strength of whatever's holding the graphene in place? Does it create heat?
So no, it doesn't create heat. So the question again is related to the longevity of graphene, right? As you increase the environmental input on the graphene, is there concern about it breaking down? What this the thing you got to keep in mind is that this phenomenon is happening at nanoscale, right? So it does work a little bit differently than what you would expect at macro scale, where you've got friction that comes into play and you've got gravity that's a big factor. So those things are different at nanoscale. The way that we're securing the graphene itself is sort of happens chemically. So there's not a concern there with that breaking down over time.
all right.
So yeah, long story short is that the key, the technology that goes into protecting the graphene is something that we're expecting these chips to last as long or longer than the electric components that are surrounding them on the printed circuit board.
Well, thank you, everyone. Thank you, Ryan.
Yeah.
Thank you, everyone online. All right.
Feel free. I'm going to be here as long as you want to talk. So I know that the online event is ending, and we'll get you the slides out.